coupling, there is a bush used, and that particular bush is going to replace the earlier one, that was the bolt as seen in this particular diagram. So our today's target is to learn how to design pin assembly. You know, bush pin type coupling is a flexible coupling. Being flexible coupling, it allows some misalignment in between the shafts. So whenever shafts are connected, a shaft may have some angular movement with respect to another shaft. So this is permitted in this coupling, so it is known as flexible coupling. This flexible coupling is achieved by means of an important element, and that important element is bush used here. Rubber bush is used, and that rubber bush is having ID equal to pin diameter, and it is placed over the pin. So when we are supposed to design the pin, what we will be doing first, we will be finding out the force acting at the pins. You know that at 4D, 4 times diameter of shaft, number of pins are placed, and how many pins are required, that also we can find from a general convention, and that convention is that when shaft diameter is less than 40, we can take 3 number of pins. N will be 3 in that case. When diameter is in between 40 and 100, you can select 4 number of pins. This is convention, but we can take higher number of pins so that a good joint in between two coupling can be achieved. Power will be positively transmitted. Figure shows number of bush located, 6 bush are there, and some torque is transmitted. Due to transmission of torque, force will be developed, and P is the individual force coming on the bush. We are supposed to find that particular force which is coming on the bush. For that sake, we will be using this relation: torque is equal to tangential force at the bolt multiplied by distance. So by this, we are in position to calculate the force acting at the number of pins, or you can say bush. So this is FD is equal to 2 times FD is equal to 2 times T, is it, multiplied divided by D. So this is the force which is coming on all the pins placed. We will be finding out that how much force is coming on individual pin, and for that sake we will be dividing this force FD divided by N. So if I divide FD, the total force acting at the pins, by number of pins used, I will be getting force acting at the individual pin, or say at the individual bush. So this is that FB force. FB force coming on each bush, say, is equal to 2 times T divided by D into N. N is the number of pins used here. So we can find how much force is acting on each pin or each bolt. This is the convention which is used to select number of pins. So if diameter is less than 40, you can select 3 pins. Same is the case for flange coupling. We will be selecting 3 bolts when diameter is less than 40. But what I suggest, you select higher number of pins or higher number of bolts, so that overall dimensions will be smaller. So for diameter 40 and greater than 40 up to 100, you can select 4 pins. If diameter of shaft is 100 and it is less than 180, you will be selecting 6 number of pins. And when diameter comes out to be 180 and more than 180 up to 240, you can select 8 number of pins. Like that is the convention of selecting pins. And our requirement is to select more number of pins naturally, so that overall force coming on pin will be less, and the dimensions of pins will be less. So we will be finding out force coming on each of the pin, and there is a empirical relation by which we are in position to select diameter of the pin. Diameter of the pin is given by D1, and that can be found by this relation. D1 is equal to 0.5 small d upon under root n. You know that d is the shaft diameter and n number of pins used. So in bush pin type flexible coupling, always we will be determining diameter by using this empirical relation. This empirical relation is important to select the diameter of the pin D1, and that is equal to 0.5 d upon under root n. Once you have selected diameter of the pin, now you are supposed to find the mode of failure of the pin. You know, pin is like this. Pin has threads provided on that diameter D1. The diameter is enlarged. You can see enlarged diameter where bush will be fitted, and this enlarged diameter and some part is fitted inside one flange, whereas this diameter D1 will be inside the another flange, and this is the head of pin, head of the pin. So we find that as this D1, this cylindrical portion is inside one flange and remaining portion is inside another flange. So it may happen that one of the flange is stationary or say unable to rotate due to very huge load. So a flange is unable to rotate. On other hand, another flange is receiving drive. So what will happen? Bolt will be cut like this. So it is failure of pin by shear. So you can see here the failure. Here probably pin will be cut, pin will be sheared off, right? This is the side view by means of which we are in position to select the area which is going to resist shear. So from this diagram we can find that tau is equal to FB, force coming on bush or say pin, divided by pi by 4 D1 square. Is it? D1 empirically we have selected. By using this relation, we will be finding out that how much shear stress will be induced in a pin if we select D1 as the diameter of the pin. So from this particular diagram, it is clear that there will be shear failure of the pin, and we have to verify that whether shear stress is within permissible limit or not. If it is within permissible limit, I mean when tau I induced shear stress is less than the permissible shear stress for this pin, we will be saying that diameter D1 we have selected is safe under shear. Now, very important part is to design this bush pin assembly. Recently we have seen pin. So this is the pin. Once again I will be telling you, pin has this diameter D1, threads are provided so that a joint will be affected in between pin and a nut. This is enlarged, D1 diameter is enlarged, so this is the enlarged diameter. It is more than D1, and pin carries head, so that pin will not be removed from other end. On one side it has a head, on other side it has threads, so that nut will be fitted. So this part will be inside one flange, whereas this enlarged diameter will be inside the another flange. Like that will be the assembly of pin. This pin always carry a bush which is known as liner. A very thin bush is used. Why this liner is provided? this liner is going to protect this pin. So manufacturing cost of this pin is high. If wear occurs at the pin due to power transmission, we are supposed to replace this pin, and replacing the pin will be costly because of high manufacturing cost of this pin. It has three different diameters, threads are provided, so manufacturing cost will be higher. So as to protect this pin, what we will be doing is a liner made up of soft material is provided. So generally there used to be a brass liner provided which prevents wear of the pin, and thickness of that liner used to be small, up to 2 millimeter. So that liner is placed over this particular pin. So as liner is provided, what will be the diameter over the liner? Diameter over liner will be D1, which is this diameter. D1 is this diameter. This diameter is enlarged. As it is enlarged, it becomes D1 plus 6 millimeter. So 6 millimeter is added for enlargement. So D1 is the diameter of pin. It is enlarged so that bush will be fitted over it. So the enlarged diameter becomes D1 plus 6. A liner of 2 millimeter is used. So what will be the diameter over the liner? It is D1 plus 6. This is the diameter of enlarged portion of the pin plus 2 times thickness of the liner. So thickness of liner, if it is 2 mm, it is 2 plus 2 into 2, is it? So it will be the diameter over the liner. Over the liner, rubber bush is fitted. That rubber bush has a minimum thickness of 10 millimeter. You can select 12 millimeter thickness, 14 millimeter thickness also. But what is the minimum thickness of bush required? 10 mm. If you select thickness of bush less than 10 mm, its failure due to bearing pressure may occur. So these are the conventions which we are supposed to use. Diameter is enlarged, 6 mm is added. A liner of soft material having thickness 2 mm is added, and over that liner there will be rubber bush. So this is the liner fitted. So over this enlarged portion, liner of 2 mm is fitted, and over that it carries a rubber bush. So this is the bush pin assembly. What will be the inside diameter of bush? Inside diameter of bush is the outside diameter of liner, correct? So D1 plus 6 enlarged diameter plus 2 times thickness of liner, DI. So DI is the inside diameter of rubber bush, whereas rubber bush has thickness 10 mm. So graphically I may say 10 mm here and 10 mm here. Thickness is 10 mm. So twice thickness will be added in diameter. So DI plus 2 times minimum thickness is 10. If minimum thickness or thickness we selected is 14, I will be adding 2 into 14. So this gives me outside diameter of liner. Outside diameter of liner will be DI, inside diameter of liner plus 2 times thickness of this rubber bush used. So please understand and keep in mind this particular bush pin assembly which we will be designing next. So as to design this bush pin assembly, this diagram from Khurmi Gupta book is helping you. What that diagram indicates? Diagram indicates this length L, which is the length of one of the flange. 5 mm is the clearance. This is the clearance in between 2 flanges. So this is one flange, and stationary is the another flange. So it is shown like that in sections. So D1 diameter portion is inside one flange, and the enlarged diameter along with liner and bush assembly is inside the whole of another flange. So you are observing here that by using nut, a joint is prepared. While designing, we have considered one failure, that is shear occurring here. If one of the flange is stationary and other is moving, bolt will get cut here, shear will take place. That mode of failure we have already considered. Now, this is the load W acting on the pin along with bush assembly. So we are supposed to consider failure, and bush is able to freely rotate over the pin. So drive is transmitted via bush. See here, there is no any permanent joint in between. We have learned earlier. See, bush is touching to another flange. So how drive is transmitted? Are you observing here? In this 5 mm clearance also, bush is seen. So when this is a driver flange, as driver flange rotates, bush is going to send power, transmit power via this friction to another flange. So bush is a transmission element and pin is going to support this bush. So bush is able to turn. As bush is able to turn over the pin, in between pin and bush, there is relative motion. See, there is relative motion in between pin and bush. Secondly, two different machine elements are there. So what mode of failure? It is bearing pressure. There are two localized compressive stresses. One is crushing, when there is no relative motion in between two components, we will be checking crushing. When two elements are in contact, like here pin and bush are in contact and there is relative motion, then criteria of failure will be the bearing pressure. So for that sake, we are supposed to verify this outside diameter we have selected for the failure due to bearing pressure. So we know that power is transmitted via rubber bush placed at the pins. Failure of bush occurs due to bearing pressure as there is slight relative movement in between pin and bush. Generally, for this rubber material, permissible bearing pressure is taken to be 1 Newton per mm square. For other materials, we can take bearing pressure higher, 2 Newton per mm square also. While designing this bush, this empirical relation is used. What is the empirical relation? Length of bush will be equal to diameter of the bush. Length, this length of the bush. I'm speaking about this length of the bush is made equal to diameter of bush, right? So diameter of bush, outside diameter of bush, we have recently selected empirically. We are now going to verify that whether it is correct or not by considering permissible bearing pressure. So this is FB, force acting at a bush. Already we have learned how to find it, 2T upon N multiplied by D, because bush are located at pitch circle diameter D. N are the number of pins used here, means that number of bush are used. So FB is the force which causes bearing pressure in between pin and a bush. So let us find out PB. PB, which is say bearing pressure. Pressure is also equal to force upon area. So bearing pressure PB is equal to force causing bearing pressure. It is FB upon area resisting. How to find area resisting? So for that sake, this diagram from VB Bhandari book is helping us. So this right hand side figure indicates the bearing pressure acting over the bush. So this is the bush. ID of the bush, dB is the outside diameter of the bush, and as bush is placed inside the flange over this particular area, I'm talking about surface area, over this surface area, bearing pressure will be working, bearing pressure will be acting. It is indicated by PM is the pressure acting over the surface. So this is, you can say, half cylindrical surface, is it, of a bush, half cylindrical surface. But we have learned in crushing, same is the case in bearing pressure. Instead of considering this half cylindrical surface, we will be simplifying, we will be projecting it on the axis. If I project this arc, project means if I extend all the points on arc on this particular plane passing through axis, I will be getting line measuring outside diameter of the bush, that is shown in this diagram. So this is the bush. Are you observing cylinder? So this is the bush shown. So this bush is projected. So as bush is projected on a plane, so dB and LB. So what will be the area? Area will be dB multiplied by LB. So bearing pressure is equal to FB upon dB into LB. So we are supposed to verify that permissible bearing pressure should be within permissible limit, right? LB is equal to dB, and dB already we have empirically selected, right? Anybody want to talk? Any problem? Presentation is visible? Is it visible?
Yes.
Okay. So don't disturb if it is visible. Any query you can ask, may type on chat box also. Now we will be solving problem on this bush pin type flexible coupling. This problem will help you in understanding the procedure which we have adopted so as to design this bush pin type flexible coupling. It is mentioned in the problem that we are supposed to design bush pin flexible coupling to transmit 40 kilowatt at 720 RPM. The starting torque of motor is 150% of running torque. Always starting torque is larger. It is given as it is 150% greater. Material selected for all, that means flange, key, pins along with shaft is 30 C8, where SYT is equal to 400 Newton per mm square. Factor of safety can be taken as 2, and permissible bearing pressure for bush material is 1 MPa. So I have this data. Power is 40 kilowatt, 40 it should be. So it is 40 into 10 raised to 3. N is equal to 720. SYT is equal to 400 Newton per mm square. SYT, yield tensile strength, is given. From this yield tensile strength, we will be finding out tensile strength, crushing strength, and permissible shear strength. So by choosing factor of safety 2, first of all, I will be finding out design strengths. You know, limiting strength and design strength. So limiting strength upon factor of safety will be the design strength, will be the allowable strength, correct? Allowable stress is equal to limiting stress upon factor of safety. For this time, I will be taking crushing stress equal to tensile stress. So sigma T is equal to sigma C, may say compressive or crushing stress, that is equal to limiting stress SYT upon factor of safety. So it is 400 given in the problem, factor of safety is 2. So maximum tensile or compressive stress for every component will be 200 Newton per mm square. Whereas We know that shear strength is half of tensile strength. So SYT upon 2FS. So it comes out to be 100 Newton per mm square. Now we will be designing shaft. We know that shaft is transmitting power, and as shaft is transmitting power, we will be designing this particular shaft for torsional shear failure by using same formula which we have used earlier. Tau is equal to TR divided by J. R is what? Distance of maximum stress plane. Once again, I will be telling you that torsional shear stress is not uniformly distributed. It is maximum at the surface. So maximum stress plane will be the surface. So distance of surface from center. So that will be radius. Correct? So R is equal to D by 2. For round section, polar moment of inertia is pi by 32 d raised to 4. So I will be putting that in equation of torsional shear stress is equal to T, R is D by 2 upon J is pi by 32 d raised to 4. So I know torsional shear stress, permissible shear stress or allowable shear stress is 100. We have calculated is equal to 16 multiplied by torque. Torque previously we have calculated. So it is 795.672 multiplied by 10 raised to 3 upon pi d cube. Earlier I have calculated this power. Power is 40 kilowatt given. That is equal to 2 pi nt divided by 60. RPM is 720. I may find torque. Torque is 530.448 Newton meter. It is said that starting torque is 150% of running torque. So we are supposed to consider maximum torque, right? It should not happen that while running it is safe, but starting it will fail. So always there will be failure of our coupling whenever motor starts. It should not happen. We are supposed to design for that torque which is maximum. So starting torque is taken to be 1.5 times greater. So that comes out to be 795.672 Newton meter. That is multiplied with 1000, that is 10 raised to 3. So it comes out to be 795,672 Newton millimeter, right? So if I put that here, I'm getting diameter of shaft as 33.15 millimeter. I will be selecting standard available. So nearer higher standard available shaft size is 35 millimeter. So I will be selecting B as 35 millimeter. So I have selected shaft diameter. Other dimensions can be found empirically, and we will be checking different stresses by considering mode of failure. So shaft diameter we have determined to be 35 millimeter. Now let us design this key. We know that tangential force is acting at a key, and that force is given by the relation torque is equal to tangential force multiplied by distance. So torque is equal to Ft is the tangential force multiplied by d by 2, which is the distance. So Ft comes out to be 2t upon d. For this problem, it is 45,466.97 Newton. This is the force acting at a key. Key is having width W and height H, length L. Key is supposed to bear this force 45,466.97 Newton. For that sake, I have to consider mode of failure. This force causes two failures. One is shear failure. In a diagram, it is shown that Ft causes shear failure. portion of a key inside a shaft will be moved, rotated with the remaining portion inside the flange. And failure diagram is shown, which shows that the rectangular area is going to resist that shear. So that rectangular area is W multiplied by L. So I will be checking shear strength, and before checking shear strength, we will be empirically selecting all the dimensions. We know empirical relation, W is equal to D by 4. So it comes out to be 8.75. We'll be taking 10 millimeter. Height, empirical relation is what? D by 6. So it comes out to be 5.83. I will be taking 8 millimeter. So rectangular key of 8 by 10 I have used. You may say I am selecting square key, so it will be 10 by 10. It is also possible. Length of key will be equal to length of hub. So it is 1.5 times diameter. So it will be 52.5. We'll be taking 54 millimeter. And now we will be checking that how much shear stress will be induced in the key. So strength equation is tau is equal to Ft upon WL. So tau comes out to be 84.19 Newton per mm square, which is less than 100 Newton per mm square. So as induced stress is less than permissible shear stress, we may say design of key is safe in shear. So shearing of key will not occur if I choose key 8 by 10 of length 54 millimeter. But another possibility is there, not by shear. It may fail due to crushing, as key is placed inside the slot of shaft. We know that whenever there are two elements in contact with each other, there is possibility of crushing. The contact area is going to resist the crushing action. So we are supposed to find that contact area. So that contact area is shown in a diagram. You can see that at the side crushing will occur. Force is going to push the key. That tangential force produced due to power is going to push the key. So key will be pushed against this wall of keyway. Is it? This vertical wall of keyway. Key will be pushed, and the contact area in between two, I mean slot and key, is this, which is highlighted by the section lines. So this hatched area is the area which is going to resist crushing. So how we can find? Height of key is h by 2. I'm sorry, height of key is h. So this will be h by 2 and length will be L. So resisting area is the contact area, which is h by 2 into L. We have selected h and L empirically. Let us find out that how much crushing stress is induced. Strength equation is sigma c is equal to Ft upon h by 2 into L. So induced crushing stress will be 210.49 Newton per mm square. But what is permissible? We have taken as 250. Okay, we have taken equal to tensile, but you know, always crushing strength is higher. It is 1.5 times 2 times sigma t. Sigma t is 100, so crushing should be 200. But for such a material which are strong one, tensile and crushing strength used to be equal. So previously we have taken equal. Okay, we have taken sigma t equal to sigma c equal to 200, but here crushing is occurring, and it is showing that design of key is not safe in crushing. We are supposed to redesign it. Redesign means what? I will be finding new dimension h. My limiting crushing stress is 200, that is equal to force causing crushing, that is tangential force, upon H is unknown. Now I am going to find H upon 2 multiplied by length of key, that is 54. So H comes out to be slightly more than selected, 8.41. So we will be accepting it as 10 millimeter. So see how we are in position to redesign or enlarge the size. Height is enlarged. So he will be now having height 10 millimeter. Let us design the flange. We know that flange has a hub section and a flange section. Hub is keyed to the shaft. So we will be empirically selecting DH, diameter of hub, as twice D, 2 into 35. So that will be 70 millimeter. The failure of hub is due to torsional shear. So I will be using this torsional shear formula, tau is equal to TR by J. And I will be finding out that how much torsional shear stress will be induced in the hub. So it comes out to be 12.6 Newton per mm square. It is less than permissible shear stress, which is 100 Newton per mm square. So I can say that whatever diameter of hub we have selected, 70 mm, is safe in torsional shear. And now I'm in position to select length of hub as 1.5 times D, which is 52.5, 54 millimeter. So length of key is taken equal to length of hub, 54 millimeter. So hub is safe. So now we are supposed to find the transverse shear stress in between flange material and that of the hub section. So you know that when flange is unable to rotate and hub is rotating with the shaft, that hub will be separated from the flange. And what is the area resisting? This surface area, is it? This is the length of surface area, cylindrical surface area, that is T, and it is cylindrical surface, so it is pi multiplied by diameter. Diameter is DH. So pi dH multiplied by this thickness. So this area is going to resist the transverse shear. Before that, we are supposed to find the force which causes this transverse shear. So force can be found by torque equal to tangential force into distance. So this tangential force will be 2 times torque upon DH, hub diameter, because I want force acting here exactly at the top surface of the hub. So FT comes out to be 22,733.78 Newton. Thickness can be chosen empirically as T is equal to diameter divided by 2. So it is taken as 17.5 millimeter. I will be keeping same, it is thickness. So I will be maintaining 17.5 mm thickness and finding out that how much transverse shear stress will be induced if I select T as 17.5 and DH as 70 mm. Previously, I have checked for shear. So tau is equal to tangential force upon pi DH T. So the shear stress comes out to be 5.91 Newton per mm square. It is less than 100 Newton per mm square. So the flange thickness, we can say whatever we have chosen is safe, is correct, and overall the flange is safe in transverse shear. So this dimension can be finalized. DH 70 mm, LH 54, length of hub is 54 mm, whereas length of flange will be 17.5. Other dimensions also we can find empirically. Pitch circle diameter is taken 4 times diameter, 140. Protection is there. You are observing that there is protection. So thickness of protection is 0.25 times D. So it is taken as 8.75. Outer diameter, as protection is provided, will be 157 millimeter, and flange thickness we have already calculated. Now we'll be using convention so as to select number of pins. Our diameter is 35. Actually, it is desired that number of pins should be 3, but we will be selecting 4 pins, so that overall dimension of pin will be small, so hole provided inside a flange will be small. For that sake, higher sizes will be selecting. We know that there is empirical relation so as to find the diameter of the pin D1. So it is 0.5 D upon under root N. So D1, the diameter of pin, comes out to be 8.75. I will be choosing nominal size 10 millimeter. So saying M10 threads are provided, M10 is the size selected. D1 will be 10 millimeter. Now we are supposed to find its failure. So we will be finding out first of all that how much is the force acting at the pins. We have chosen 4 pins only. It would be better if we have selected 6 pins. So diameter will be less than this 10 millimeter. So the torque causes tangential force also at the pins. So torque is equal to Fd multiplied by capital T divided by 2. So Fd, which is the force acting at all the pins, will be 11,366.74 Newton. This force is coming on all the pins. So I'm supposed to find what is the force acting on each pin, or say each bush. So that total force 11,366.74 divided by number of pins 4. So every bush, every pin is subjected to tangential force of 2,841.68 Newton. Now we'll be designing this pin. We know that there is shear failure. So this threaded portion is inside one flange, whereas the enlarged portion is inside another flange. This flange is going to push it, whereas another flange is stationary. So likewise, force is acting, causing shear failure. So diameter D1 will be sheared off. And what is the area resisting? It is pi by 4 D1 square. Is it? So tau is equal to force coming on individual pin upon pi by 4 D square. D is 10. So that shear stress will be 36.17, which is less than permissible. Okay, 100 Newton per mm square. So you can say that pin diameter we have chosen is correct, and pin is safe in shear. Now we'll be designing this bush pin assembly. We know that the diameter is enlarged. So enlarged diameter will be D1 plus 6. D1 is 10. So enlarged diameter will be 16 millimeter. Pin always carry liner made up of soft material. It is softer than material of pin, so that wear will occur of the liner. Liner we can easily replace, and cost of liner is less. And usually thickness used to be 2 millimeter. So what will be the diameter over the liner? It is 10 plus 6, 16 is the diameter. This diameter, enlarged diameter, is 16. Over that 2 mm liner is there. So as liner is placed, we can find that over the liner it is 16 plus 2 on one side, 2 on other side. So will be the diameter 20 millimeter. So inner diameter, inside diameter of rubber bush Di will be 20. Correct? Usually 10 mm thick rubber bush is necessary. I will be choosing 10 mm itself. So it comes out to be 40 mm. outside diameter of this bush, this diameter, outside diameter of bush is 40 millimeter, and you know that diameter of the bush equal to length of the bush. So diameter of bush equal to length of the bush, and this diagram shows that bush is subjected to force which causes bearing pressure. So we have chosen length of the bush equal to diameter of bush. Permissible bearing pressure given in a problem 1 Newton per mm square, and bush has some relative motion with the pin. So criteria of failure is permissible bearing pressure. So actually bearing pressure will be working over this half cylindrical area, but we will be simplifying it by projecting on a plane passing through the axis. See, in this particular diagram, your concept of projected area will be clarified. Actually, area is this half cylindrical area. This half cylindrical area I am talking about. This half cylindrical area is made planar, correct? So it is projected on a plane. So when you project it, half cylinder, say, what will be projection? Projection will be this. Height will be dB, and this length will be LB. So projected area is dB multiplied by LB, area of this rectangle. So bearing pressure is equal to FB upon dB LB. If you put that, bearing pressure is coming out to be 1.77. What is the permissible bearing pressure? It is 1 Newton per mm square. It shows that if you select diameter of bush as 40 millimeter, its failure will definitely occur, as permissible bearing pressure for that rubber material is 1 Newton per mm square. What to do now? We are supposed to choose diameter again. So what we will be doing? We have taken thickness of rubber bush as 10 millimeter. It is minimum thickness. We have chosen minimum thickness so as to say save material or cost. I will be choosing larger size now. So I will be selecting 14 millimeter. 14. Now chosen 14 millimeter. So what will be outside diameter of bush? 20 inside diameter plus 2 times 14. 14 to the 28 plus 20 will be the 48 millimeter. So I will be taking dB 48. I will be taking LB as 48, and again I will be finding bearing pressure. That will be simpler task. PB is equal to force upon 48 into 48. So it should come below 1 Newton per mm square. Is it? So this is the way of finding out dimension of the bush. Okay. Otherwise, what I can do, you know, put PB equal to 1. Put PB equal to 1. 1 equal to force upon dB into LB. Both are same. So PB is equal to force upon dB square. Correct? Find dB. Whatever dB you get, you will be finalizing as the outside diameter of the bush. Are you understanding this procedure? As bearing pressure is more, failure of bush will take place due to bearing pressure. For that sake, either I will be increasing thickness, putting it here, again finding bearing pressure. It should be less than 1 Newton per mm square. If it is not, I will be again increasing thickness, taking 16 mm thickness. Again, I will be finding PB, and PB should be less than 1 Newton per mm square. That is one. Secondly, what I can do, I will be redesigning it. PB is limit 1 Newton per mm square. So 1 is equal to force coming on each bush upon dB into LB. we know that empirically length of bush is equal to diameter, outside diameter of bush. So it is dB square. So dB square is equal to 2841.68. So square root of that will give me dB. So I will be choosing next standard available. So thus we have learned how to design this bush pin type flexible coupling. I hope that you have understood the complete procedure of designing this bush pin type flexible coupling.